This diagram outlines the simplest deployment model: application, database, and cache run on a single server. A browser contacts a DNS, translating the domain into an IP address. The device then sends an HTTP request to the server, which returns the response. This monolithic structure works for a few hundred users, but if traffic spikes to tens of thousands of concurrent requests per second, the system breaks. The server exhausts its available compute resources, and the application goes offline entirely. The first reaction to increased traffic is vertical scaling, adding more CPU and RAM. However, a server's motherboard has strict physical limits. You cannot add unlimited memory or processors to a single piece of hardware. Once you hit that hardware ceiling, the only viable methodology for continuous growth is horizontal scaling. Instead of upgrading one machine, you add more servers to a shared resource pool. True reliability requires anticipating limits, removing single points of failure, and distributing the workload. This schematic illustrates the first step in horizontal scaling: tier separation. We extract the database from the web server and place it on a dedicated machine. Decoupling the compute layer from the storage layer allows engineers to isolate bottlenecks and scale the web tier independently. At this storage layer, the type of database matters. While relational SQL databases are standard, scaling often requires evaluating NoSQL alternatives. If your datasets are highly unstructured, or if the application requires ultra-low latency serialization, a NoSQL data store is often the superior architectural choice. Returning to the web tier, allowing users to connect directly to the web servers introduces a severe choke point. If a server reaches its maximum concurrent connection limit, any subsequent users trying to access the site will simply drop offline. This diagram introduces a load balancer. Placed at the front, it intercepts ingress traffic and distributes it evenly across web servers using private IP addresses. This creates immediate redundancy. If server 1 fails, the load balancer instantly routes all new traffic to server 2. While the front-end web tier is now distributed and protected from node failure, this specific architecture still routes all generated traffic back to a single database. The data tier is now the system's primary structural choke point. A solitary database cannot survive a hardware crash. Under high traffic, it cannot process massive throughput of concurrent read and write operations quickly enough. This architecture utilizes master-slave replication. Data-modifying commands, inserts, updates, or deletes, route exclusively to the master database. The master then copies that new data to multiple slave databases. Since applications read more than they write, read operations are distributed across the slave nodes. Segregating read and write operations radically improves system performance. It prevents heavy write transactions from locking up tables and allows the system to process a massive volume of read queries in parallel across different machines. It also creates an automated failover protocol. If the master node suffers a catastrophic failure, the system automatically promotes a healthy slave node to take its place as the new master, ensuring zero downtime. Implementing database replication ensures data permanence, prevents data loss during localized hardware destruction, and guarantees uninterrupted read availability for the end user. Even with an optimized database, forcing a system to repeatedly query the hard drive for identical, frequently accessed data introduces an invisible latency tax on load times. We introduce a local cache tier. The server checks the cache first. If missing, it queries the database, writes the result to cache, and returns it. To prevent stale information, a strict time-to-live expiration policy purges old data, ensuring subsequent requests pull fresh data. Heavy static assets, like high-resolution images, video files, and CSS style sheets, present a different latency problem. Forcing a user in Europe to download a large image from a centralized web server in California incurs a heavy geographic transit penalty. This flowchart details a content delivery network, or CDN. When a user requests an image, the local CDN server performs an origin fetch from the main server. Once cached at the edge, it intercepts subsequent regional requests, returning the file instantly from local storage. Offloading repeated database queries into memory, shifting static assets to edge networks, ensures sub-100 millisecond response times. This schematic illustrates a stateful architecture. A user's session data is stored directly on the individual web server that processed their first request. The load balancer must use sticky sessions to route all subsequent requests back to that exact server. If it fails, the session data vanishes. This stateless architecture fixes the routing problem by removing user session data entirely from the individual web servers. Session data is extracted into a persistent, shared NoSQL data store. Now, any available web server can simply fetch the necessary state data from this shared central storage. This map outlines a multi-data center deployment for an international user base. Incoming traffic is intercepted by a GeoDNS service. GeoDNS analyzes the user's physical location and routes their requests to the absolute closest data center, splitting the global traffic load geographically. If a massive power grid failure takes an entire data center offline, the DNS layer executes a 100% failure reroute, directing all global traffic to the remaining healthy data centers. Back inside the healthy servers, another invisible bottleneck occurs during heavy compute tasks. Synchronous background processes, like rendering a customized photo, tie up the web server's response threads, blocking it from answering new incoming requests. To decouple execution time from client response time, engineers institute a message queue. The web server drops the heavy processing job into the queue and returns to answering new users. Independent worker pools then pull jobs out of the queue and execute them asynchronously. Extracting session state into a shared NoSQL data store and pushing heavy compute processes into asynchronous message queues removes the final internal restrictions, enabling infinite, friction-free compute scaling. Look at the full transition. What began as a brittle, monolithic server has evolved into a micro-distributed ecosystem. A single request enters, and the system coordinates instantly. The load balancer absorbs the front-end traffic, routing users to an available stateless web node. The independent cache tier intercepts repeated queries before they hit the hard drives, while master-slave replication cleanly divides heavy database reads from writes. Deep within the architecture, message queues allow worker nodes to chew through background computation without interrupting the main flow. This finalized architecture can scale infinitely. When a specific resource hits its limit, you no longer need to upgrade the whole system. You simply provision more instances exclusively at the layer where the bottleneck is detected. Scaling from 0 to millions of users is not achieved by procuring stronger hardware. It is achieved by anticipating exact failure limits and architecting highly decoupled horizontal layers designed to outlive them.